Okay, thank you for the introduction. I'm Davide Faccialá from EFN, CNR, and Politecnico di Milano in Italy. And the title of my presentation is Probing the Giant Resonance of Xenon by Two-Color High-Order Harmonic Generation Spectroscopy. So I will start introducing you to the giant resonance in xenon probed by high harmonic generation spectroscopy, and then we generate high-order harmonics driven by two-color field to probe this giant resonance. I will show you the experimental setup and two different experiments where we change the relative polarization between the two colors. So two different configurations, parallel and perpendicular polarization. And at the end, I will show you the results and the interpretation for both experiments. So what is the giant resonance of xenon? It is a huge enhancement of the spectrum, which is located at 100 eV here, and was first observed by Scheiner in the group of François Legaré and Villeneuve. And they interpreted in this paper this giant resonance as a multi-electron effect that can be described using the usual three-step model used to describe high-order harmonic generation. So in the first step, the electron is ionized from the outermost valence shell. Then it is accelerated by the laser field, and at the end, it recombines with the ion. And if the electron has enough energy, in xenon, it can recombine via two different channels. In the first case, it can recombine directly with the 5p hole, while in the second case, it can inelastically scatter with 4d electron that is promoted to the 5p valence shell, and then the electron recombines with the 4d hole. This multi-electronic behavior was then confirmed by many-body calculations made by Stefan Pabst and Robin Santra. So we generated high-order harmonics, as I said, in a two-color laser field. The first color has a wavelength of 1500 nanometers, while the second color is its second harmonic generated inside a beta BBO crystal. And we use a calcite plate to synchronize the two pulses, and a pair of fused silica wedges to fine-tune the phase delay between the two fields. Thank you. So with this pair of fused silica wedges, we change the phase delay between the two fields, and at each phase delay, we acquire a spectrum from our XUV spectrometer. And we can switch between the two possible polarization configurations. In the first case, the polarizations of the two colors are perpendicular to each other, while we can use an halfway plate to switch to the parallel polarization case where the two colors have the same polarization. So we start from the parallel configuration case. In this case, the driving field is modulated and the symmetry between the two half cycles is broken. So the upper cycle is no longer equal to the lower cycle. And this results in two different sets of trajectories, the red ones and the blue ones, with two different cutoffs, and as you saw in a previous talk, with two different ionization probabilities. In the right figure, we can see that for the upper cutoff trajectories, we have the low ionization probability, while for the lower cutoff trajectories, we have a high ionization probability. That means that if we see in the spectrum, here retrieved by Frolov, this paper, we expect to see only this lower branch, while the upper branch is suppressed because of the low ionization probability. And another interesting effect of this experiment is that if you can see this crossing point between the two cutoffs, we can estimate which is the intensity of the fundamental field alone. So we made an experiment in xenon. We acquired several spectra at different phase delays. And if we focus on only one oscillation, we can see that there is an enhancement of these contributions. And we can compare this with theoretical calculations made by Stefan Pabst in the time-dependent configuration interaction single scheme. And as you can see, if we only consider that the 5p shell is contributing in the high-order harmonic generation process, then this upper branch is suppressed. While if we consider that 5p, 5s, and 4d orbitals are interacting to each other, then there is this enhancement, and the theoretical results are in very good agreement with our experimental results. So we can see that the giant resonance, in this case, counteracts for the reduced ionization probability of these trajectories, making them visible in the spectrum. But we want to know more about the process, about this process. So we switch to the perpendicular configuration case. So in this case, the second harmonic acts as a gating, which selects specific trajectories with a given energy. So we can do a map between the photon energy and the phase delay between the two fields that maximizes the harmonic emission. So this is a very simple classical picture, and you can see if I change the phase delay between the two fields, then only one classical trajectory recombines with the ion. So if we look at the quantistic approach, in the strong field approximation, the single active electron approximation, and saddle point approximation, we can retrieve which is this phase at each photon energy for both long and short trajectories. And if we consider both, what we expect to see is that phase that maximizes the harmonic emission as a function of the photon energy must have a monotonic behavior and a positive slope up to the cutoff, because here we should see only the contribution of the short trajectories, while beyond the cutoff we expect to see a monotonic behavior and a negative slope. However, SFA tells also us that beyond the cutoff there is an exponential decrease of the intensity of the field, so we usually see a sharp cutoff. So we expect to see only this contribution of the short trajectories. We made the experiment in xenon, and in fact what we saw was that there is a clear change of this slope at 65 eV. So we thought that at 65 eV there is the cutoff. The cutoff must be placed here. And in fact, if we compare this with the theoretical calculations in the single active electron approximation, there is a fair agreement. However, we want to be sure about this, because if the cutoff is here, that means that we can see non-classical trajectories beyond the cutoff. So to be sure about this, we made another independent measurement, where we do an experiment in xenon in a parallel configuration and perpendicular configuration with the same experimental conditions and intensities of the fundamental and the second harmonic field. And as I told you before, in the parallel polarization experiment, this crossing point can give us an estimation of the fundamental field. And this means that it can give us an estimation of where the cutoff is in the perpendicular configuration experiment. And we can see that the cutoff should be here where there is this change in the phase. So this demonstrates that, yes, in perpendicular configuration, we can see photons beyond the cutoff, where single active electron picture predicts an exponentially decreasing signal. So knowing this, we found also that there was a discrepancy of the experimental phase with respect to the single active electron phase. In particular, we can see here another change of the slope at 72 EVs. To reproduce this change in the slope, this discrepancy, we want to include the multi-electronic effect inside the model. And what we did was to take the dipole amplitude and the phase from random phase approximation with exchange calculations made by Kayfetz for a photoionization process. And knowing that a photoionization process is the inverse process of an electron recombination in a high harmonic generation, we can take these two terms and put inside the action as a phase term. So we extend the saddle point approach for this new modified action that takes into account the multi-electronic effects. So if we do this in a perturbative approach, we can find that the recombination times are changed with respect to the previous one by a factor which is this tau d. And this time we expect to be of about 20 attoseconds. That means that we expect that the electron recombines earlier with the ion with respect to the single active electron picture. So if you consider this modification and these new recombination times in our model, we can see that the new phase, which is the blue one, reproduces very well what we see in the experiment. In particular, we can see here this change in the slope that reproduces well what we see. So we can see in the experiment, basically, that the electron effectively recombines earlier than what we expect in a single active electron picture. And also, we could reproduce quantitatively the minus 20 attosecond delay in the giant resonance region. To summarize, so the giant resonance allows you to see a unrevealed feature. In the parallel polarization case, it allows you to see this upper branch, so it counteracts for the reduced ionization probability of those trajectories, while in the perpendicular polarization case, it counteracts for the reduced probability to find an electron in a classically forbidden region beyond the cutoff. And in the perpendicular configuration, we could also determine which is the delay in the region of the giant resonance. So we had an experimental signature of this reduced recombination time, and we can make an attosecond measurement. I would like to thank my group, in particular Salvatore Stagira and Caterina Vozzi, and also our collaborators, Stefan Paust and the group of Nirit Dudovic. And thank you all for the attention.